This is chapter 8.3.3. We're going to motivate DFT by decomposing a signal into sum of sinusoids, which is what basically Fourier transform is doing. It's decomposing a signal into a sum of complex exponentials. We then show that actually DFT can be recognized as an orthogonal decomposition in linear algebra subject. Finally, we show the analysis and synthesis equations and give one example. Let's motivate. Assume that we have a signal called x of t, and here this is continuous time. And in this particular example, x of t is described by a sum of complex or a sum of cosine wave with frequency omega and phase shift at that particular frequency scaled by a magnitude. And in time, this is that rate graph that we are showing, the signal of interest, and it is composed of two cosine wave, one here and the other one a smaller one with amplitude 1. And you see the x of t is equals to f1t plus 2 plus f2t. This is called the time representation because in the horizontal axis we have time, and in the vertical axis we have the signal's amplitude. So basically we have an array of numbers describing this signal, and if it's continuous time, of course we can't really remember all the points. Now, this is continuous time signal representation. How is it like to represent in the frequency domain? What does it mean when we say we want to represent the signal in the frequency domain, which is basically what Fourier transform is doing? Well, first you have to recognize that these two blue dots can be sketched in this way in a three-dimensional plane, where now we have time in this axis, the amplitude in this vertical axis, and now we have one more axis stretching out, which is called the frequency. And we now also can realize, of course, that hey, we can visualize these two blue dotted lines as two separate signals, one at one frequency called omega 1 and the other one at omega 2, right? Which is exactly what xt is. One of the signal is at 5, omega equals to 5, and the other one is omega equals to 10. Now, when we say that we want to represent a signal in the frequency domain, what do we mean? Look at these two spectrum. The word spectrum means basically the horizontal axis is the frequency, and the y-axis is one is a magnitude spectrum, and one is a phase. So what does this magnitude spectrum reveals to us? It says that hey, at omega 1 equals to 2 pi 5, there's a cosine wave with amplitude 2, and there is a cosine wave at omega equals to 10 with amplitude 1. The magnitude spectrum reveals what the red line can be broken down into. There is two cosine wave at different frequency with different amplitude. But as you know, amplitude alone is not enough. We need the phase as well, because look, in the equation describing x of t, we have 2 cosine 2 pi phi t minus pi over 4. So we need the frequency, we need the amplitude, and we need the phase. So you see that at this point, we have the frequency, the magnitude, as well as a phase, which is minus pi over 4. For omega equals to 2 pi 5. And omega equals to 2 pi 10, we have amplitude is 1, and the phase is plus pi over 6. So you'll realize that in the phase spectrum, the horizontal axis is frequency, the vertical axis is phase, and in the magnitude spectrum, the horizontal axis is frequency, and the vertical axis is magnitude of the cosine at that particular frequency. So with that, with this understanding, basically is we are given a red line or a signal representing in time. We want to actually generate this and this figure, the magnitude and the phase spectrum. This process is called Fourier transform, converting a representation in time into representation in frequency. Thank you.